Hello dear students, let us find the balance condition of Wheatstone Bridge with the help of Kirchhoff's laws. As shown in this diagram, this is the Wheatstone Bridge circuit. It consists of four resistances P, Q, R and S. A galvanometer G is connected between diagonal points B and D, and a voltage source is connected between next diagonal points A and C. With the help of variable resistance P, if the current in the galvanometer is made zero, that is Ig becomes zero, then the bridge is said to be balanced. Now the current distribution in the circuit is shown in the diagram with Kirchhoff's current law, that is KCL. Here I is the current flowing from voltage source, and at point A it is distributed in two parts, I1 and I2. I1 reaches at point B. Because Ig is 0, therefore again I1 comes in this direction. Similarly, I2 comes in this direction because Ig is 0. Now, in closed loop A, B, D, A, Kirchhoff's voltage law gives sigma EMF. This loop has no EMF source, therefore sigma EMF will be 0. I1P clockwise minus I2R. Sigma EMF is equal to I1P minus I2R. This gives I1P is equal to I2R, equation 1. Similarly, in closed loop BCDB, in this closed loop, sigma EMF is 0. I1Q clockwise positive minus I2S anti-clockwise negative, that is I1Q is equal to I2S. Question 2, question 1 upon question 2 gives P upon Q is equal to R by S. Question 3. Question 3 is the required balance condition of Wheatstone Bridge. Now we take the meter bridge. Meter bridge is shown in figure 1. Meter bridge is used to find out the resistance of given wire and the resistivity of its material. It is based on the principle of Wheatstone Bridge. This is figure 1 represents the meter bridge and figure 2 represents Wheatstone Bridge. Here dark strips represent the metal strips with almost negligible resistance. The given wire of unknown resistance P is connected in one gap. Known resistance with resistance box is connected in other gap. Potential difference is applied between points A and C. This is a metal wire of uniform cross section area and of length 1 meter, fitted on a wooden stand which is provided with a meter scale. A galvanometer is connected between points B and D. One end of galvanometer is connected, one end of galvanometer G is connected at point B, and other end of galvanometer is connected between jockey, which is a slider key. A potential difference is applied between ends A and C of wire. Wire is of length 1 meter. By sliding the jockey on this wire, we find the null deflection in the galvanometer. In that case, this meter bridge circuit becomes a balanced Wheatstone bridge. Now we can compare meter bridge with Wheatstone bridge. Between A and B, we have resistance P. Between B and C, resistance Q. Between B and C, resistance Q. Between A and D, resistance R. L1 length of wire acts as resistance R. Between C and D, resistance S. L2 length of wire acts as resistance S. Given unknown resistance P is connected in one gap, and a known resistance with resistance box is connected in second gap. One end of galvanometer G is connected at point B, and the other end of galvanometer is connected with jockey, which can be moved on the wire. A potential difference is applied between ends A and C of wire with a cell. By adjusting the value of known resistance Q with the help of resistance box, we find the null deflection galvanometer. If L1 and L2 is the balanced length on the meter bridge wire, then from the principle of balanced Wheatstone bridge, P upon Q is equal to R upon S gives P upon Q is equal to R means L1 into R, S means L2 into R, where R is the resistance per unit length of this wire, meter bridge wire. So R gets cancelled. We get P upon Q is equal to L1 upon L2, because L1 plus L2 is equal to 100 cm or 1 meter. Therefore, L2 will be equal to 100 minus L1. So, P upon Q is equal to L1 upon 100 minus L1. Therefore, from question 1, unknown resistance P will be equal to Q times L1 upon 100 minus L1 . Question 2, with equation 2, we find unknown resistance P of given wire. If rho is the resistivity of wire of resistance P, then resistance is directly proportional to its length and inversely proportional to cross section area. Therefore, P will be equal to rho L upon A. Therefore, rho will be equal to P A upon L, or rho will be equal to pi r square into P upon L. Question 3, where r is radius of given wire measured with screw gauge and small l is the length of given wire between these two connected points. So, with the help of equation 3, we can also find the resistivity of given wire.